Great, thanks. So thank you very much to the organizers for inviting me to speak. I'm really sorry I can't be there in person. That's due to travel around my own significant birthday. But it's really a pleasure to be speaking at the meeting for Kobe and Sergey. A lot of my work has taken place in the beautiful setting that they created of complex analysis in O-minimal structures. But in this talk, there'll be no O-minimality or indeed no model theory, no point counting, and no Diophantine problems directly appearing, although this topic is very much somehow an outgrowth of those ideas and closely connected to Zilber-Pink type Diophantine problems, and especially Ax-Schanuel theorems. So I hope the slide moved. Yes. So I'll be talking about joint work with Jacob Tsimerman, and there were two motivations for this. One was to explore somehow Ax-Schanuel properties and when we can expect a differential equation or a collection of differential equations to have an Ax-Schanuel property. And the other motivation was the Massa-Zanya work, series of papers on elementary integrability of abelian integrals, that should say, really not abelian functions, but abelian integrals. And they do this by somehow reducing this problem. In fact, it's a classical thing to Zilber-Pink type problems. And I guess the question was, we're going from elementary integrability to Zilber-Pink problems. Is there an Ax-Schanuel connection? So I'm going to first talk a little bit about the classical topic of elementary integrability, which is about when does a given function have an elementary primitive or antiderivative. So this is also sometimes called integration in finite terms. And maybe the most famous result in the subject is due to Liouville in 1835, when he proved that things like the error function e to the x squared and the logarithmic integral, integral of dx over log x, are not elementary functions. And elementary here means essentially that you write downable in closed form using log, exp, and algebraic functions, starting with x. So having log and exp, we'll see it's a slightly funny definition. And I think it's really motivated by the idea that we have explicit names for those two functions, the log and the exp. Now, by an algebraic function, if I say that u is an algebraic function of v or of some vi's, I'll simply mean that as functions of x, that u satisfies some non-trivial polynomial relation over the vi's. In other words, that u is algebraic over the field of complex numbers with the functions vi. And so in that sense, algebraic functions are not so explicit. We don't have explicit names for every algebraic function. And I think some presentations of integration in finite terms do restrict to using roots, nth root, square roots, cube roots, some explicit root. In other words, that you can write down your integrand using buttons on your scientific calculator, but it really is more natural to allow all algebraic functions. So again, here's a more formal definition. I'm going to work throughout in fields of meromorphic functions in some one variable, in some disk. One could frame everything in terms of differential fields, but it's easier just to somehow stay in the complex realm. Later, at some point, I'll be talking about algorithms. And when we talk about algorithms, we'll still talk about complex functions and disks and so on, but we'll really imagine that we're working in an explicitly given field of finite type, so that we know who's transcendental, that we know explicitly the field we're working in. So let's suppose that z of x is a regular function of x on some disk in the complex plane. We say that z is an elementary function, or is elementary, if there is a finite sequence of non-constant functions, xi and zi. So these are really pairs, finite sequence of pairs of non-constant functions, possibly on some smaller disk. And they have the following properties: that for each I, dzi, so that's a typo, it should say dzi dxi is 1 over xi. So zi is, if you like, the logarithm of xi, or xi is the exponential of zi. And either xi or zi is algebraic over x and the previous pairs. And finally, z is algebraic over the field generated by x and all the xi's and zi's. So that means you can somehow write down z by a sequence of taking something algebraic over what you've got, then adding either its exponential xi, or its, if you took zi to be algebraic, or by adding its logarithm zi if you had taken xi algebraic over what you had, and eventually z is algebraic over that. And so that's a picture that we'll see several times, this picture of these, well, generators of field extensions. So, for example, the result of Liouville is that if z is the logarithmic integral of x, then there is no such sequence on a disk in the complex plane. But, for example, an example due to Abel from the Massa-Zanya paper in Acta Mathematica 2020, you have this seemingly elliptic integral, which is actually elementary. And here it is explicitly. Now, just to settle some terminology, on the left-hand side, we have the primitive of an algebraic function, and I'm not going to worry. I mean, I see already on this page at the top, I wrote that here, z is the integral up to x, and I used a dummy variable. Here I've written it without the x and the dummy variable, but I mean the same thing. And we're not going to worry about the constants of integration, which don't actually affect anything. So on the left-hand side, we have the primitive of an algebraic function. Such a thing is called an abelian integral. If you write y squared equals x to the fourth plus 2x squared minus 4x plus 1, then this integral is of the form of 5x minus 1 over y dx. It's the integral of a meromorphic differential on an algebraic curve. And here that's the elliptic curve, y squared equals x to the fourth plus etc. And in general, you can go backwards and forwards between those things. Every integral of an algebraic function can be rewritten as an integral of a meromorphic differential on an algebraic curve. So some remarks. Firstly, of course, the primitive of a rational function is always elementary. That is the method of partial fractions that we all have fun with in high school. The logarithmic integral is not an abelian integral because it's not the integral of an algebraic function. And the key result that Liouville used, this theorem of Liouville, is a very general theorem about existence of antiderivatives in elementary extensions. So it says that if you have any field F, differential field of meromorphic functions, so closed under differentiation, and X is an element of that field, then if you can find an antiderivative Z of X in some elementary differential extension field, then in fact you can always do it in a very specific way, that you can find x1 up to xm and some v in the field and constants ci, such that x is the sum of ci dxi over xi plus dv. And in other words, if you integrate that z, the antiderivative of x, is really just the linear sum of these logarithms of the xi's plus something in v. So in other words, that you can integrate x by just taking logarithms, no exponentials, and of course adjusting perhaps by some element of the field f. So just some further remarks that Hardy in 1905, in his book on the integration of functions of a single variable, has a passage discussing the integration of algebraic functions where he says that no general method has been devised by which we can always tell after a finite series of operations whether a given integral is really elementary or elliptic or belongs to some higher order of transcendence. Now, the elementary part of this was solved, and even more generally by Risch in 1970/2022. So he sketched in 1970, Risch sketched an algorithm to decide if an elementary function has an elementary primitive. And again, when we talk algorithms, we always imagine we're in some finite type explicitly given field. So Davenport in 1981 explicates this method and even implements it for abelian integrals. So this is an algorithm that will decide whether an abelian integral is elementary. And this entails a certain divisor constructed from residues being a torsion point in the Jacobian. Now, I just want to go back to the 2022 here, because Risch somehow sketched this algorithm, but he only really described it fully in the case of fully transcendental elementary functions. And he had some unpublished manuscripts that have been published this year in a book edited by Michael Singer and Clemens Raab. So this is an algorithm that will decide this question, not only for abelian integrals, but for any elementary function. So you can iterate logs and exps and algebraic things, and then you can ask, is that thing elementary? So Masser and Zanya, in a series of papers, explored elementary integrability for a one-parameter family of algebraic functions, or if you like, for a one parameter family of curves and differentials. And because of this torsion point condition in the Jacobian, so you have this moving family of curves and a moving family of differentials, and that gives you a moving family of divisors in these Jacobians that have to be torsion. And so this connected with their work on relative Manin-Mumford problems, which are, well, part of the Zilber-Pink conjecture, the general Zilber-Pink setting of Diophantine problems. And in this, culminating in this 2020 paper in Acta Mathematica, and they refute the conjecture that had been made that in such a family of differentials depending on a parameter t, that this is elementarily integrable for infinitely many specific values of t, if and only if it is generically elementarily integrable, i.e. that you can integrate it, so to speak, identically in t. So it's very interesting that there are counterexamples to this. And it's also quite interesting, and I would say not fully explicated exactly what is the connection of this with Zilber-Pink type problems. But their analysis does go through Zilber-Pink problems. So our work is in a somewhat different direction. So what we want to do is, if you like, admit more or different primitives other than the logarithm as the primitive of 1 over x as elementary. So our general problem is, if you have some abelian integral z, the integral of an algebraic function alpha of x, so here alpha will satisfy the algebraic, will satisfy some polynomial relation with x, a of x, alpha x equals 0. When can you construct such a primitive using the primitives of some other specified algebraic functions, which we'll call the BJs? So the algebraic functions BJs will be, if you like, roots of the polynomials capital BJ. So here, capital A and capital BJ are simply complex functions in two variables, and the alpha and the BJs are the algebraic functions defined of x or of t defined by those polynomials. And formally speaking, we want to ask, when is there a sequence of pairs of meromorphic functions? So here x will be a regular function on some disk. When is there a sequence of pairs of functions xi and zi such that for each I, dzi dxi is an algebraic function of xi is one of the defined by one of the capital BJs, that either xi or zi is algebraic over previous things. So we're again allowing the use of the primitives of the algebraic functions or their inverse functions. And z finally is algebraic over the x and all the xi's and zi's. And we call this exceptional integrability. So that's by analogy with elementary integrability. We'll say that in this case that alpha of x is exceptionally integrable using the BJs. Now, I just want to make a few points about this definition. Firstly, you can use each BJ more than once. As you could in the case of elementary integrability, you could take the logarithms of several things and even repeat taking logs. So here again, at each I, we allow the use of some bj, but it can be the same j for different i's repeatedly. I also haven't specified which branch. So in this area, there can be issues with branches, but I haven't restricted which branch I'm using. And it's actually a fact that you can prove through differential algebra that I have specified alpha as being a particular algebraic function, but if alpha is exceptionally integrable using the b's, in other words, using some branches, then in fact any other branch alpha of the relation defined by A is also exceptionally integrable. So this is somehow really only about the polynomials, the A's and the capital B's. But you may need to use different branches and repeated branches. Okay, so that's the definition of exceptional integrability. And basically our results are firstly that there is an Ax-Schanuel connection, there is an Ax-Schanuel statement, if you like, for individual abelian integrals or collections of abelian integrals. And that using that one can give a criterion and a decision procedure for when A, or the algebraic functions determined by A, are exceptionally integrable using the abelian functions, or the functions defined by the B's. And we'll also be able to answer a suitable interpretation of Hardy's problem of when is a given abelian integral elliptic. So, okay, so to describe the Ax-Schanuel connection, I'll return to Schanuel's conjecture. So here, if Z1, it should be up to Zn. There's no Zn. The Zn is missing here. If Z1 up to Zn are complex numbers and Xi's are exponentials of the Zi's, then Schanuel's conjecture asserts that the transcendence degree of all the Xi's and all the Zi's over Q is at least n, unless the Zi's, which are the logarithms, are linearly dependent over Q. So that's, of course, very much an open conjecture, but in 1971, Ax proved a functional analog of this conjecture, also conjectured by Schanuel, which is called the Ax-Schanuel theorem. And he proved it in various forms for power series and in differential fields, and I'm just going to state it for fields of meromorphic functions. So let x1 up to xn be regular, not identically or even non-vanishing functions of t on some disk. And of course, if the xi's are not identically zero, you can always move to some smaller disk where they're non-vanishing. And the z1 up to zn, some determination of their logarithms so that they satisfy the differential equation dzi dxi equals 1 over xi. Then the transcendence degree over C, over the complex field of the field of functions generated by the xi's and the zi's is at least n plus 1, unless the zi's are linearly dependent over Q mod C, meaning that there's a non-trivial relation sum of qi zi equals C, where the qi's are rational numbers, not all zero, and C is a complex number. And I want to note the importance of this plus 1. So we don't just get transcendence degree n, as in Schanuel's conjecture, but n plus 1. And the plus 1, if you like, is for the variable t. And that's because the transcendence degree of one pair, x and log x, z equals log x, is 2. So every time you add one more pair, your transcendence degree has to go up by at least 1. Of course, however you do it, unless you add, unless you violate this linear dependence over Q mod C condition. So that is Ax-Schanuel theorem. So some generalizations. So Ax in 1972 gave a second proof of his theorem in the setting of complex algebraic groups, from which you can deduce a version for complex semi-abelian varieties. And Kirby in 2009 gave, a version of Ax's 1971, the differential field proof of the exponential case in the semi-abelian setting. So Bertrand in 2008 observed that, in fact, Ax's proof works more generally for connected commutative complex algebraic groups with no vectorial quotients. No quotients being just an affine line. But abelian integrals of the type we're going to consider lead to generalized Jacobians, as studied by Rosenlicht, and also see the book by Serre. So when you have, I'll talk a little bit about this further below, but if you have a curve x and a modulus m, meaning a non-negative divisor, where you allow some poles of your differentials, you get a generalized Jacobian, j sub m of x, using all the meromorphic differentials to that modulus. And when you take m to be empty, you get the Jacobian. And in general, you get covers of the Jacobian by either multiplicative or additive extensions. And sometimes, even if your given differential is not an exact differential, so by an exact differential, I mean has an algebraic primitive, that the corresponding Jacobian may involve some exact differentials. And so you end up in a world of possibly groups that have that do have vectorial quotients. So abelian integrals lead you into this slightly wider world of commutative connected complex algebraic groups, which might have vectorial quotients. But it's actually quite easy to make the adjustment, because essentially what you see is that if you have a particular modulus, you'll have a certain number of exact differentials to that modulus, differentials that have, if you like, whose primitive is an algebraic function. So if you like, the logarithm, the corresponding generalized logarithm is an algebraic function. But if you subtract off those, then what you get is a non-vectorial group, and you can apply this Bertrand version of Ax's theorem, and you can get an Ax-Schanuel for a general connected commutative complex algebraic group. And I'm not going to state that, but I'll sketch how we go through that to get an Ax-Schanuel theorem for abelian integrals. So I apologize a little bit for the notation here. In the application, we're going to have an algebraic function defined by some polynomial capital A. So I'm here going to call that A0. And we're going to ask whether this is integrable in terms of some other complex polynomials, which I was calling B sub j. So I'm going to here call those A1 up to AK. So you've got to imagine that, and they can, of course, repeat. I'm not saying that these polynomials are different, but now I imagine I have K plus 1 polynomials, capital A0 up to AK, and some functions xi and zi, non-constant regular functions on some complex disk in the complex plane, all functions of the variable t, with the property that the zi's, if you like, are the corresponding abelian integrals of these algebraic functions. So capital AI of little xi and dzi dxi equals 0. So dzi dxi is some algebraic function of xi. And the statement is, again, that we've got K plus 1 pairs. So the statement is that the transcendence degree of all the xi's and the zi's is at least K plus 1 plus 1, unless, if you like, the zi's are linearly dependent. But now this linear dependence is over C, and somehow modulo algebraic functions whose derivatives are algebraic functions, well, to the corresponding modulus. So, I mean, for the purpose of the theorem, let's say that they're just algebraic functions, but they are somehow in a limited space that we'll see comes up in the proof. Now, of course, we can say rather more about this linear relation, and actually it does correspond to a relation coming from a coset, a non-trivial coset relation in some suitable generalized Jacobian. But since we don't introduce those until the proof, we'll just state the theorem like this. And somehow we can't assume here that the CI's are rational numbers because I haven't normalized these abelian integrals in any way. So if you could take well, somehow if you can prove that they're actually algebraic numbers, but without normalizing them, you can't know that you might have how your the coset structure is described. Anyway, so that's the theorem, and here's a sketch of the proof. So we view the zi's as integrals of some differentials omega I on some smooth projective curve capital Xi, which has little xi as a uniformizer. So what that really means is that you introduce some additional algebraic variables over the xi's so that you have a smooth algebraic curve and you have a meromorphic differential on that curve that you can integrate locally and make your function zi. And of course, introducing all these extra variables yi doesn't change the transcendence degrees of the fields. And we can also assume that each omega I is an inexact differential, or the conclusion is immediate, that you just immediately have that condition just on that omega I, that it has an algebraic primitive. So then you choose some moduli on each curve so that the omega I is a meromorphic differential to that modulus, and you extend to a basis of the linear space of differentials on the curve xi to the modulus mi modulo exact things. So if you like, we'll just take a basis of the inexact things. And then there'll finally be some exact differentials that can, well, I see I'm missing a bracket. But conveniently, the bracket should be, actually, where should the bracket be? It should be around there. So, and then you can form the generalized Jacobian. That, of course, does involve these exact differentials. So it has, if you like, corresponding vectorial quotients that will eventually quotient out. And you form the product of all those generalized Jacobians and its Lie algebra. And then the X and Z locally give you a complex analytic locus locally in this product of generalized Jacobians and its Lie algebra. And if the conclusion of the theorem fails, if the transcendence degree is at most k+1, then what happens is that you take your k+1, these differentials, the omega i's, there are k+1 of those, you add in the rest of the basis, but you subtract the k+1 that you already, of the omega i's. And the sum of those things is just the sum of the hi's, which is the dimension of the non-vectorial quotient of the ith generalized Jacobian. But that sum of hi's, of course, is less than hi+1, which is what you always get in these Ax-Schanuel statements. And so by Ax-Schanuel for the generalized product of generalized Jacobians, this locus lies in a coset of a proper, non-trivial proper subgroup. And here proper non-trivial means it's a subgroup of the non-vectorial part. It's not just a sort of lying with the exact stuff. And so by Ax-Schanuel in this setting, you do get a relation on all the zij's, some linear relation, mod exact stuff. But in fact, this relation has to be on the given differentials, because otherwise you can, so to speak, repeat on the subgroup. If these omega i's are linearly independent in the sense of the theorem, over the complex numbers, mod exact things to the differentials, then you can look at the smallest coset that they lie in, complete them to a basis, and apply Ax-Schanuel there, and you get the same calculation that the transcendence degree is too small. So you actually must get a linear relation on the given zi's. So that is the Ax-Schanuel theorem for abelian integrals. And of course, this proof goes through a product of generalized Jacobians, but in some sense, it's a standalone Ax-Schanuel on any set of a finite set of abelian integrals. And we'll see another formulation of it in a little bit. So now I want to go back to exceptional integrability, and this following calculation is really the key calculation that connects exceptional integrability to Ax-Schanuel. Because what happens if the algebraic function alpha, the algebraic function alpha defined by the polynomial A and its abelian integral z is integrable using some xi's and zi's that come, which are abelian integrals defined by the capital Bj's. So then you have some sequence of pairs xi, zi. And if you look at this diagram now, we've got x and z, and we've got x1 up to xk, and z1 up to zk. So we have k plus 1 pairs of arguments, x and xi, and their abelian integrals, z and zi. But what is the total transcendence degree of all these functions? Well, you get x, that's 1. And then for each pair, xi, zi, one of them is algebraic over the previous stuff. So you get at most one more for each I. So you get k plus 1, and then z is algebraic over all those functions. So you only get k plus 1. And in other words, exceptional integrability implies that you are in the exceptional case of an Ax-Schanuel statement. And this means that your locus of x's and z's.
Jonathan, can I ask something?
Yes.
But why do you say that the zi's and the xi are interalgebraic? You only have the derivative of zi algebraic over xi.
Yes, only the dz dxi is algebraic. Sorry.
Somehow in the counting you said that the zi is algebraic over xi or something like that.
Yes. No, that's the definition of exceptional integrability. You start with x, and then either x1 or z1 is an algebraic function of x, and the other one is determined by the differential equation.
I see.
And then you can add something else that's, one of x2 and z2 is algebraic over all of that. And then you have either its abelian integral or abelian logarithm.
All right.
So at each stage, one of the functions is algebraic over the previous ones. That's the definition of exceptional integrability.
Okay. All right. Yeah.
And then at the end, the z finally is algebraic over all of that stuff. So you end up in a non-trivial subgroup of this product of generalized Jacobians. And, well, unless you really didn't need some of these functions, the coset has to be dominant to each factor, because the curve, a non-trivial point on the curve always generates the generalized Jacobian. And so, so this somehow projects down, but it may project to a coset on the xi's that is of dimension greater than 1. If it is of dimension 1, that means that all of the xi's are algebraic over each other. But it may have dimension bigger than 1, and in that case, you can re-choose your xi's to be a curve in that higher dimensional thing. So at the cost of choosing new xi's, you can take the xi's to be algebraic over x and the z to be linear over the zi's, again, modulo algebraic functions whose derivatives belong to suitable moduli. And so that gives us a criterion, if you like, that if alpha of x, which again is an algebraic function defined by some polynomial a, is exceptionally integrable using some bj's, then there is a finite sequence of xi's and zi's such that, again, for each I, dzi dxi is algebraic over xi in one of those relations bj, but now 2 prime, each xi is algebraic over x. So before we had the condition that either xi or zi is algebraic over x, and 3 prime z is linear modulo exact, C-linear modulo exact algebraic things in the zi's, rather than just being algebraic over the whole lot. So we can compare this with Liouville's theorem. So again, if you like, you only need logs. So to go from X, you just append algebraic things, take their abelian logarithms, and then you're linear over that. So you again never need exponentials, so to speak, to do your exceptional integration. Now, Liouville's theorem, which maybe I won't go back to now, but is much more general because it tells you about any antiderivative of a function in a differential field that lies in an elementary extension, whereas our theorem only deals with abelian integrals, not the integral of anything, because we don't have an Ax-Schanuel for anything in the world. We only have it for abelian integrals. On the other hand, our theorem doesn't need this very special form of algebraic dependence that you go up one step at a time, adding one degree of transcendence. And our theorem would be the same if you just said, I have all these x's and z's, and their transcendence degree is at most k plus 1. It doesn't have to have this structure of a sequence of one-dimensional extensions. So that's kind of interesting, and I'll come back to that at the very end. Oh, which is coming up faster than I thought. All right, sorry. So, okay, but that's really the key calculation, that exceptional integrability puts you in the exceptional case of Ax-Schanuel. Now we can reformulate this in terms of curves and differentials, and we can always realize the zi's as integrals of meromorphic differentials omega I. And then the xi's being algebraic over x means that there's a correspondence between these two curves. And the condition for integrability can be reformulated in the following way, that you have exceptional integrability of omega naught, if you like, or its integral z naught, using the zi's, integrals of the omega i's, if and only if omega naught is in the C-span of differentials, which you get by taking trace images of the omega i's, pulled back and pushed onto x0 under any correspondences from the xi's. So from x naught, you look to each of your curves xi. You look at all the ways you can pull back the differential omega I, pull it back and push it under the correspondence. And then you ask whether omega naught is in that C-span, and this can be decided by an algorithm. You have to somehow compute the Néron-Severi group, which you can do in the case of curves, or if you like, decompose all the Jacobians and find representatives for all these pullbacks. We can also answer Hardy's question in the sense that given an algebraic function alpha of x, you can decide whether you can integrate it using the primitives of all meromorphic differentials on all elliptic curves. And that amounts really to computing the Jacobian of this thing and splitting it up and seeing whether your differential, so to speak, lives only in elliptic factors. If it lives in elliptic factors, you're good. And if it lives on other factors, then you lose. And you can do this also in genus 2 and 3, but not 4, because then not all abelian varieties are Jacobians, and you get some more difficult questions coming up. And again, there seem to be some interesting questions about the relation between Liouville's theorem and the Ax-Schanuel for abelian integrals. There is an elliptic Liouville theorem in the literature due to Hebisch just a couple of years ago. But more generally, you can ask about an abelian Liouville. There are generalized Liouville theorems with error functions and so on, or about extending Risch's algorithm to more general families of abelian integrals. So finally, of course, a very happy birthday to Kobe and Sergey. So it's customary in Jewish culture to wish people on their birthday until 120. But since they already achieved 120, we'll have to go for 240, and with much more practical and structural model theory along the way. So thank you very much for your attention.